Hello, Professor. My name is Priyang. My team is 19. I'm here to walk you through my final project of 255, which is accelerate inference of state-of-the-art solution with TensorRT. Let's get started. As you can see over here, we're going to discuss about state of the algorithm that I perform, comparison of those algorithms, TensorRT inference on those state-of-the-art algorithms, and comparison between the TensorRT models with time and throughput. And I'm also going to discuss about the failures that I faced during this particular whole project. As you can see over here, state of the algorithms, I did perform all of those in TensorFlow. MobileNet version 1 of 50 layers and input size is 160. I performed that algorithm first. And as we down, if we go down through top to bottom, I stop at ResNet version 250, which is the last one. And you can see, uh, you can see over here, I try to perform like minimum 10 state-of-the-art algorithms that are available on TensorFlow platform itself. And we're gonna discuss their accuracy and their results in the next slide. Over here, as you can see, MobileNet version 1 give us the accuracy, training accuracy of 95, validation accuracy of 96. It uses 12 GB of RAM and it's type of a TensorFlow. TensorFlow 2 preview, which is a small version of a MobileNet version 2, which gives a 95.57% accuracy and validation accuracy 68.02, which is also takes 12 GB of RAM. If we move down through that particular models, the ResNet version 2 of the 50 layer of the feature vector gives the training accuracy 99.77. On top of it, the validation accuracy 96.94, which is almost 77. And as you can see from top to bottom in ascending order, we only had that particular algorithm with the highest validation accuracy in the TensorFlow. I also tried to perform LXNet version 10 from the PyTorch on the same image data set, and it's far more better than any other trained model I used in the TensorFlow. I don't know the reason, but yes, because they all are pre-trained. I don't know why PyTorch has the LXNet so powerful or accurate, but it is well indeed. The validation accuracy is 99.29. It also uses 25 GB of the RAM, which is also a type of a PyTorch. Now, the ResNet version with the layer 101, which is 100 layers. Basically, ResNet is 152 layers, we all know. But the smaller version of it, which is 101 layers, it's also not working for me in my Google Colab because it's required 25 GB, more than 25 GB of the RAM. Same for the Inception and MobileNet version 3. So as you can see, we're going to perform our TensorRT inferences on MobileNet version V1, which is the first one, and the last one, which is the ResNet version 250, just to look at it, how they perform in two different algorithms, how they behave, what's the changes, and to compare between those two algorithms for the inferences. Now, let's look at the ResNet 50 TensorRT inferences for 1000 pictures. The result for the time is the TensorFlow model itself by default takes the 50 seconds or 51 seconds. The floating point version 32, floating point version 16, and integer 8, which is the data type of the whole particular data model, takes significantly very less. As you can see over here, integer 8 took almost 10th time, which is the 1/10th time of the whole particular model. That's what we want. Why? Because when we train our model, we have to deploy that particular model into some small hardware where we're going to perform our own live project, for which we really need our high speed to take live video as a like more pictures, because 1 minute pictures, sorry, 1 second frame has like 1 minute frame has a lot of pictures in it. That's why if our inference is high, we can process the video more higher speed than the normal TensorFlow model. That's why this inference is needed. On the right hand side, as you can see, the inference time taken by the integer rate is significantly very low as compared to FP32 and FP16. The throughput gives the same. The integer 8 tower is the very high pillar because it has the highest capacity to do the throughput in the ResNet, which is 1431 pictures per second. And 1/10 of that, which is TensorFlow model, which is just 157 pictures. Now, if we talk about the MobileNet V1 version for the TensorFlow inferences, we see almost the same thing. TensorFlow model takes 45 minutes, and integer 8 take 140 seconds. Sorry, 45 seconds, my bad. And the integer 8 takes 140 seconds. The thing is, integer 8 should be significantly lesser than FP16 and FP32. But over here, as we can see, the integer 8 is higher than FP32 and FP16. The reason is, I don't know why. The thing is, it does change and it's significantly near to the FP32 and 16, but it's almost the same. On the right hand side, we cannot see the difference because it's like hardly a few milliseconds difference, not at all 1 second difference over here. In a throughput, we can see easily because FP32 has 5,940 pictures around, but FP16 is reduced 5,909 pictures only, and integer 8 is significantly decreasing regarding both of two, which is 5,886. This kind of a behavior might be because of the model structure. That's what I wanted to highlight over here. Every different model has their own different structure, and depending on that, they perform their calculation. Over here, floating point 32, floating point 16, and integer 8 are the data types that are performed on by default data graph generated by the TensorFlow model. The horizontal and the vertical model try to compact the data calculation by replacing the data type of original data type to floating point 32, 16, and integer 8. The thing is, they do not change the structure, they just accelerate the structure. So even though they had to pass through the like 100 layers, now over here they have to maybe pass through the like 50 layers with a smaller data type, which significantly increase the speed of the inferences. But it does not change the structure. The structure of the TensorFlow model is exactly as same as the integer 8. Now, if we compare between those two models, as we can see, the ResNet version to TensorFlow version takes 51 seconds, but the MobileNet version takes 45 seconds. And integer 8 for the ResNet take 5.6 seconds, but in the MobileNet, it takes 1.4 seconds. The thing is, it's also, again, the structure of the model. ResNet structure, as you can see, is just like a bottleneck, bigger to small, same thing. But MobileNet separates its structure and process parallelly. That's why MobileNet is very famous for the speed. That's why I wanted to show, or I wanted to try and set the benchmark for my data set, like how it performs on a MobileNet versus the best accurate model for my data set, which is ResNet right now from the TensorFlow Hub. Over here, the image are almost around 6,000 for the MobileNet version, but the images throughput for the ResNet is maximum 1,431, which shows the complexity of both the structure and the speed of both the different model. Now, let's talk about my failure. In a starting, I just wanted to do the PyTorch version ONNX and then convert that ONNX into the TensorRT. The thing is, the way PyTorch version converts to the ONNX, it's not even able to process ONNX version into a TensorRT. I even tried, asked a lot of people, put my reviews on a forum. A lot of people had the same doubt, but they are not even able to solve, or no one helped me. So I had no option, but I had to shift to the TensorFlow to perform the TensorRT. But I also tried to work on the Docker, just like you mentioned, Professor, but in a Docker, I only get 3 GB of the RAM, for which I can only load the pre-trained model from the PyTorch, which is significantly less weighted than my own model. I wanted to run inferences on my own model, which is 250 MB, but the pre-trained model is significantly very less. Just because I trained it by myself over here on different data set, that's why it's big. I don't know. But the thing is, it's not even able to load in the memory while it performs for the inferences. So I was also a failure over there for performing in a Docker. I might be doing something wrong. It was my first time with the Docker, but again, I asked my few friends, but they are not able to help me. That's why I had to shift to the TensorFlow. Now let's look at my Google Drive structure and the code. That's the end of the slides. And as you can see, I'm going to share my Google Drive structure, Google Drive link in the submission, and that's how it's going to look like. I have my final report over here, the presentation I'm giving, I just gave right now, which is over here. And as you can see, my all three implementations, from which let's see the ResNet folder, in which you can see the code and all the outputs. And this is the same model for the ResNet. If you go to the ResNet, in a starting, you can see over here, I did take the help of the NVIDIA TensorRT example model for particular running TensorRT on a TensorFlow, which is which is pretty basic. Find the GPU we have it or not, install the GPU 2.0. After that, we can see the loading of the data that I took from the Kaggle. I use the data set, which is our this signboard data set from the GTSRB, German traffic sites, from the Kaggle. After loading the data, build the model. Over here, as you can see, I have set my directory for the model. I split the data. After splitting the data, this is the magic thing. The thing is, if you wanted to change or perform state-of-the-art models, you can find it on a TF Hub. TF Hub, which is the TensorFlow Hub, as you can see over here, TensorFlow Hub. This is the example for the ResNet version 250. I have attached all the links that I perform every single model in the report. And as you can see, this particular ResNet version 52, which is trained, and this is the checkpoint where it takes all the trained data set and train the last layer only according to our own data set. That's why we have to save all the checkpoints, and as soon as it pickups from the checkpoint to train only the last header for our own data set. Over here, we say trainable, which is equal to false, which is we don't want to train the whole data set. We want to freeze the first part and then just going to train the last part. The input size is 224 by 224. And just because it's a color image, that's why it's a 3-dimension. And the last layer activation, which is a softmax. But certainly you can train your own, you can put trainable is equal to true. So which is going to learn the whole thing from the start to bottom. Everything will be trainable. RAM requirement will be high. The process requirement will be high. If you have the enough big amount of data set, then only they prefer us to use this trainable is equal to true. But if we perform in our own small models, they recommend us to use the trainable model. Trained model, pre-trained model. After that, as you can see, we run the inferences. This is the graph. Why graph looks so weird? Because it just trains the last layer. Most of the layer, it's a freeze, which is already trained. That's why it just started from one point, it looks like, and it's going nowhere, just parallelly. That's the constraint for this particular, all the pre-trained model for the TensorFlow, I guess, because I got the same result in all the models. But the ResNet gives really good accuracy if we do compare with other different models, which is almost 77. Now let's look at the TensorFlow 2 inferences. I load the model because that's the model I saved, and that's the model we can see over here. Loading the model, doing the prediction. After doing the prediction, I did the throughput. In the throughput, it gives 157 images as we see. The 60, almost 51 seconds for whole throughput. for 1000 images, of course. As you can see over here, I did it for 1000 images. And yes, even after training it, I was losing my GPU and I had to install TensorRT version 5th. That's why I had to redo process over here after the training the model. I don't know why, but that's how I found as a glitch or something, but it works for me. So that's why I just reinstalled the GPU over here because it was losing after the training. I install, we have 5th version, and I follow the NVIDIA TensorRT. I told you before. Uh, that was the basic tutorial I follow. Uh, we have 32. This is the throughput of the 32, significantly very less time and very good amount of throughput. FP30, FP16, almost same throughput, same time. But the magic comes here over here in integer 8. Integer 8 is taking too much long time. It was very hard to convert. I don't know, but every single time it drops the runtime. It loses the runtime and fool the RAM, something like that. I had to retrain the whole thing, but luckily I able to make it together and I performed the integer 8, which is so fast, only 5.6 seconds for 1000 images, and the throughput is 1431. As you can see over here, this is the comparison graph, time graph, and the throughput graph. That's what we saw. Now, let's look at the PyTorch implementation. For the PyTorch implementation, this is the model. This is the training and validation split. After that, I tried to perform LXNet by myself from the PyTorch itself, but I was facing a lot of issue for settling the parameters further down for the training. That's why I did like pre-trained model of the PyTorch version 10 from the LXNet PyTorch. Again, the Torch hub load, just like we did TensorFlow hub, it's a Torch hub. The good thing is this particular algorithm is so accurate for this particular model. The reason is I don't know why TensorFlow algorithm is not giving this much good accuracy. The validation accuracy is 99.30%. I tried to convert this particular model into the ONNX model, and I did convert ONNX model, but after converting ONNX model, as you can see, model has been converted to ONNX. So I saved that particular ONNX model, and as you can see, if you go to my PyTorch, it has its models, which is ONNX model and PyTorch by default to PTH model. But what I was not able to do, which was run the ONNX runtime, get the model and convert it to the TensorRT. I faced even a lot of problem to do install PyTorch TensorRT into the Colab, but I might be able to do the same thing in the Docker. I was able to, but I told you I was facing a lot of issues in the RAM. The RAM was full and I was not able to load my pre-trained model, which I just show you over here. That PTH model was not able to load over there to convert it into ONNX and further to convert it into TensorRT. And so far so good, that's it. So the runtime, the ONNX runtime gives the issue over here. And I filed a complaint or did raise the issue in the TensorFlow, PyTorch community, but I haven't got any response. It's been 1 month. So pretty much that's it. And you can find my all trials and everything over here in their individual folder. Thank you so much, Professor.